Okay, so part 2 of counting principles is permutations and factorial notation. So probably should have been called factorial notation and permutation. So factorial notation is a concise representation of the product of consecutive. I think it would point this out. Consecutive descending natural numbers. So the definition n, so this is red factorial, n factorial, is n times n minus 1 times n minus 2. So you just keep subtracting numbers until you get down to 3 times 2 times 1. So for example, 5 factorial is 5 times 4 times 3 times 2 times 1. Okay, so we start at the number, then we just work our way down. We evaluate 4 factorial, or 4, but I have to say 4 factorial. Get excited about it. 4 times 3 times 2 times 1, which is 24. 10, or 10 factorial. 10 times 9 times 8, 7, 5, 4, 3, 1. Oops, somebody want to work that out? What do we got? One or two working away. What is it? Read it to me. 36288. 3628. Another 8. So 3,628,800. 7. Okay, 7 factorial over 6 factorial. So let's think about this. If we go to expand it, we'll get 7 times 6 times 5 times 4 times 3 times 2 times 1 on the top. And on the bottom, we're going to get 6 times 5 times 4 times 3 times 2 times 1 on the bottom. So instead of actually having to work it out, what's it going to be equal to? So what's it equal to? 7. Just plain 7, not 7. It's just 7, right? So the idea being, okay, wait, this 7 factorial means something, right? This 6 factorial means something. And if we expand it out, then we can see, well, 7 times 6 times 5 times. Now, there's actually another way to think of that, too. We can think of it like this. So if I'm going to write out 7 factorial, I'm going to go 7 times 6 times 5 times 4 times 3 times 2 times 1. But do I have to write out 6 times 5 times 4 times 3? Basically, what I'm saying here is you can expand 7 factorial, and you can stop anytime you want. So you can go 7 times 6. I'm done. Just put down the factorial sign. We could write that 7 factorial. So we've got the full thing, right? So I could go 7 times 6 factorial. Or I could go 7 times 6 times 5 factorial. Or I could go 7 times 6 times 5 times 4 factorial. So the idea being, I can stop writing a factorial anytime I want. I just start out with the term, multiply it by the next lowest number, and when I decide I'm done, I just put down the factorial symbol, right? Just throw down an exclamation mark, you're done, right? And it's equal, right? They're all equal. Because 7 times 6 times 5 factorial is 7 times 6 times 5 times 4 times 3 factorial, and so on. So let's use that idea in doing part D. So in D, I'm going to expand 8 factorial. So I write 8 times 7 times 6 times 5, and I'm tired. I'm going to stop. Now, why did I stop there? Because that's the expression we have in the denominator. It's 5 factorial. So I start expanding 8 factorial, stop at 5 factorial, these guys cancel, and I just have 8 times 7 times 6, which is 56 times 6, which is 6, 336 maybe? I don't know, try and find out. 42 times 8, yeah, 336. So 8 times 7 times 6, should I keep going or stop? Stop there, right? Well, I stopped it. Well, okay, so down here we've got 2 factorial, 6 factorial. Not that we draw well, but 2 factorial, 6 factorial. So we stop when we get an expression that we already have, right? So remember, we can stop any time. 8 times 7 times 6 times 5 times 4 factorial. And the way you stop, you just throw down an exclamation mark. So now we have 8 times 7 over 2 times 1, which is 28. Okay, so we can evaluate that. Okay, you give F a try. We'll start with 9 factorial, start expanding it, decide when you're going to stop. So we can stop any time, but it's got to be a reasonable place to stop. Cross those off, put in a 1, right, to show that you canceled it. We get 9 times 8 times 7 times 6 over 3 times 2 times 1. Now, 3 times 2 times 1 is 6. And we're left with 9 times 8 times 7, which is 72 times 7, which is 504. Yeah. Okay. Thanks for verifying. It was 7 times 70 is 490, and then 14. Okay. Any question on that? It's factorial notation. Right. Then we'll get into the, so why, okay, great, it's a way to do things, but why? But first, we're going to do some more. Write the following, so what is 6 times 5 times 4 times 3 times 2 times 1? 6 factorial, right, equals 6 factorial. Uh-oh, what's 11 times 10 times 9? Well, if we kept going, what would it be? It'd be 11 factorial, right? Now, what part is missing out of the 11 factorial? So we've got 11 times 10 times 9. So if I was writing 11 factorial, and I went 11 times 10 times 9 times, and I decided I'm going to stop, what would I be writing? 8 factorial. So what does that mean? Well, okay, wait, let's think of this. It's 11 times 10 times 9 times 8 factorial, but I'm going to get rid of the 8 factorial. So let's just write this. So the top is really 11 factorial, and the bottom is the 8 factorial. So if we write 11 factorial over 8 factorial, okay, just go backwards. So I wrote 11 factorial over 8 factorial, go up a line, right? And we would say, if you wrote that, it would be 11 times 10 times 9 times 8 factorial, because we're going to stop there. We're going to cancel those out, which means, oh, we just end up with the 11 times 10 times 9. Okay, give this one a try. So think, what would it be? What's missing? How would I write this 13 times 12 times 11 times 10? And if I decided, all right, 13 times 12 times 11 times 12. That's going to be 13 factorial. And then think, but what's the part that's gone? What would I write on the bottom? Well, 5 factorial is the 5 times 4 times 3 times 2 times 1. But what else goes on the bottom to get rid of 9 factorial, right? So 13 factorial over 9 factorial is going to be this. And this, that's just 5 factorial. Okay, so if we wrote out 13 factorial over 9 factorial, we would end up with 13 times 12 times 11 times 10, right? The 9 factorial is now gone, top and bottom, and we've got this 5 factorial left over on the bottom. Okay, let's generalize. So number 3, we're going to generalize this thing. So n factorial over n minus 1 factorial. Okay, so we know what n factorial is, right? Right up at the top of the page there, n factorial. So here's how we simplify these. Start with the larger expression. So is n bigger than n minus 1 or vice versa? It's kind of a ridiculous question. Is n bigger than n minus 1? Yeah. So we start with the larger expression. And we say, okay, I can write that as n times n minus 1. Now, I could go on to n minus 2, but I can also stop anytime I want. So is now a good time to stop? Well, the bottom is n minus 1 factorial. So if I stop, those cross off, and I just get an n. So you can think of it, what if that was 5 factorial over 4 factorial, right? You'd go 5 times 4 factorial. You're just going to stop here because I have the expression top and bottom. They cancel. Okay, so that's what's going on here. N plus 4 over n plus 2. Which one's bigger? N plus 4, right? I mean, and if you're in doubt, just throw a number in there. So, well, if n is 10, that's 14, that's 12. Okay, 14 is bigger. Okay, so I can start the top off. Stop here or keep going? Okay, now remember we go down by 1 each time. So what's next? N plus 2. Stop here or keep going? Okay, stop here because that's the expression we have in the denominator. So we're going to expand the larger expression, right, the larger factorial, until we hit the smaller one, right? And we do that, we just go down 1 each time. So we start with that. Okay, these guys cross off, and you get n plus 4 times n plus 3. And if we expand that, we would get n squared plus 7n plus 12. So factorial is a shortcut, right, for multiplying consecutive numbers, starting at a particular number and going down until we get to 1. Okay? And in a little while, we'll see why does that thing exist, right? I mean, it's like if I go 2 plus 2 plus 2 plus 2 plus 2 5 times, right? We could do that, but we can also say you've got 5 of those 2s, right? So multiplication is just a shortcut for repeating addition, right? 2 plus 2 plus 2 plus 2 plus 2. You can say you're adding 5 2s. We go 5 times 2. That's a shortcut. This is a shortcut. What's bigger, n minus 5 or n minus 4? N minus 4. Here's what we do. We're going to put the n minus 5, the smaller one, up top. We're going to start with the bigger one, n minus 4. Then we go down. What's the next number down? N minus 5. And then what do? So we stop. Right? Anytime we stop the expansion of a factorial, we just put down the exclamation mark, right? The factorial symbol. And we get 1 over n minus 4. So we take the larger. If you're not sure which one's larger, just throw in a number. All right, look, what if I put 10 in there? Then up top I got a 5, and on the bottom I got a 6. Okay? The bottom is bigger. That's the one we're going to expand. Right? We start with that expression, and then we just keep subtracting 1 until we get down to 1. So for something like this expression, n would have to be bigger than 5. Right? You can't have a negative. Solve for n where n is a natural number. Okay, so let's take the left side of this and do what we did up above, right? Like really directly above. Say n times n minus 1. Okay, wait, that's equal to the denominator. Cross those off. Solve. We just get, oh, well, then n is equal to 12. Who's bigger, n minus 2 or n minus 3? N minus 2 or n minus 3? All right, well, so if n is 10, then the top would be 8, the bottom would be 7, so n minus 2 is bigger. How do we expand n minus 2? We go from n minus 2, next, n minus 3, stop or go on? Stop. Right? So we take the bigger one and we start expanding it until we get the smaller one, and then we stop. Okay? And the way we stop, our stop sign is an exclamation mark, which just says factorial. We cancel these guys. N minus 2 is 10. What's n? Add 2 to both sides, you get 12. Next one, who's bigger, n plus 2 or n? I know, it feels as wrong asking that as it does. Okay, so we're going to leave the n factorial on the bottom, right? Because we know that's the small one. We're going to start with n plus 2. Then we're going to multiply by what? N plus 1, right? Go down by 1. Okay, do we stop at n plus 1? Nope. Okay, what's next? N. Then we stop, right? Because that n is, well, when we stop, that becomes n factorial, right? Denominator, we've got n factorial. These cross off. These multiply. All right, so we have some work to do here. We're going to have to solve a quadratic. So we have n squared plus 3n plus 2, after we multiply out the two binomials, is equal to 42. Okay, we can solve these. It's half of math 20, right? It's working with quadratics. So n squared plus 3n minus 40 is 0. And here's one thing about factorials. They're always going to factor, because n is always an integer. Okay? We don't know that yet, and there's no particular reason why it should be, but I'm telling you right now. So n is always an integer. So n plus 8, n minus 5 equals 0. And here's one other thing you don't know. N is not just always an integer, actually. N is always a natural number. Okay, that's a lie. N is always a whole number. Okay. And why that is that comes in the out of order part. So when we do permutations, we'll explain why. N is always a natural number. So any negative number we just reject. Because the problem is, if you take a negative number, negative 8, right, you go one less is negative 9, then negative 10. You're never going to get down to 3 times 2 times 1. Okay? So n has to be a natural number. Right? It's a counting number. And the reason is why we use this n factorial. And that is permutations. So what is a permutation? It's an arrangement of distinguishable. What does distinguishable mean? You can tell them apart. Okay? You can tell one from the other. So an arrangement of distinguishable objects in a definite order. So I can tell the things apart, and they can be arranged in a certain order, and I can always tell them apart. So order matters. That's what you're going to see with this, right? So for permutation, order matters. Because in a day or two, we're going to learn about something else where the order doesn't matter, right? And you might think, well, why does order matter in one case and not? So if I deal you a hand of cards, does the order you get the cards in matter, or are you going to pick them up and you're just going to pick them up and arrange them any way you want, right? You don't care what order they came in. You can say, I'm playing this particular game, so I'm going to arrange my cards in a certain manner. If I'm playing a different game, I'm going to arrange them in a different order. Okay? But I don't care what order they came in. Okay? In a permutation, the order that things come in matters. So, the letters A, B, and C can be arranged in 3 factorial, right, which is 3 times 2 times 1, 6 ways. So there's 6 different ways we can arrange A, B, and C. That is, there are 6 permutations, right? Permutation, distinguishable arrangement. And here they are. ABC, ACB, BAC, BCA, CAB, CBA. That's the only ways they could be arranged. Now, the way I do it, you could draw a tree diagram to do this, right? Because you could say I could start with an A or a B or a C. And if I start with an A, then I have a B. Let me show you what a tree diagram would look like. Sort of review. So first letter, second letter, third letter. So my first letter could be an A, a B, or a C. If my first letter is an A, my second letter can be a B or a C. If I have an A and a B, then I have to have a C. If I have an A and a C, then I have to have a B. If I have a B, I can have an A or a C. If I have a C first, it could be an A or a B. If it's CA, it's got to be a B, and if it's CB, it's got to be an A. To get all the arrangements, we trace out each branch. So this branch is ABC, ACB, BAC, BCA, CAB, CBA. So that's one way to get those arrangements, right? It's also a review of last lesson, right? Tree diagram. Also, if you're going to list them, because you could just start randomly throwing down letters and then see how many arrangements you get, but you're probably going to end up repeating something. So the way this is done, it's very systematic. It's like, let's start with A. All right, let's go in alphabetical order. So I got an A, then a B, then a C. Okay, well again, let's start with A. Well, all I can do is flip the last 2, so it's ACB. Start with an A, all right, I've done all the arrangements to start with A, right? It's either ABC or ACB. Let's start with a B, go in alphabetical, BAC. What's left? Then BCA, and then so on. Okay, so it's good to have a systematic way of doing these, right? Not so much with these 6, right? Like, you know, if you accidentally repeated one, you're just kind of writing them out at random, you'd eventually come up with the 6 different, right? Different or distinguishable arrangements. Okay, but if you're just writing them at random, you're probably going to end up repeating something once or twice before you realize, oh wait, I've already written that one, right? Cross it out, let's try a different one. How many permutations can be created in each case? 4 students line up for a group photo. Well, here's another way. Oh, let's go back to ABC first. Right? So that's a tree diagram. A tree diagram gives you the sample space. The sample space is the universal set theory, right? Or the set of all possible outcomes. That's the definition of a sample space. We have listed all the 6 arrangements. What if we don't want to list all the arrangements, but we just care about how many? Then we think, all right, to get how many, I'm going to use the fundamental counting principle. So the fundamental counting principle says we are arranging 3 objects. Okay? And you can just think of them as Scrabble tiles. You got a tile with an A, a B, and a C. And we have these 3 objects, so the first, the second, the third. So how many choices do I have for the first object? I have 3. For the second object. For the third object. I didn't do that, so. Good. So we have three choices for the first letter. It's either an A, a B, or a C. Oh, look at the tree diagram, right? We have three choices for the first letter, then two choices for the second, then one choice for the third. And 3 times 2 times 1 is 6. So if we start getting like 10 letters, where there could be a lot of different arrangements, we don't want to list them all, right? We just want to know how many ways can this be done. So a sample space is used not only if I need to know how many ways something could be done, but I really want to list them. So you think about the uniforms, right? Maybe I just want to imagine each of the different uniforms that we could do with the red top, the white, the black. So I want to list them all, right? And say, we're not going to do that one. It's not going to look good. Okay, but we have a choice then. But if we just want to know how many, fundamental counting principle. All right, how many permutations? 4 students line up for a group photo. Okay, how many choices for the first student? 4. Then, what's another way to say 4 times 3 times 2 times 1? 4 exclamation mark. Which, if you like, you could say it as 4. You can emphasize it, or 4 factorial. Either way, which is 24. Right? So we get the actual number. So 4 factorial, more correctly. 4, if you want to be excited about it.
5.
Yeah, this one. So the arrangements of the letters decay, right? So we have 5 letters that are all different, right? And they have to be all different, right? Remember, it's a distinguishable arrangement. And actually, in the coming days, we'll learn about what if they aren't different, how many arrangements are there? We'll figure out how do we figure that out, right? How do we calculate that? We obviously do not want to list all of these arrangements, right? Because there are how many of them?
5.
Which is 120. Is it time to introduce the shortcut yet? Is it time? Do you want to see the shortcut? All right. So, you can see why we would have this factorial notation now, right? I want to arrange 3 letters. Well, 3 times 2 times 1 says the fundamental counting principle. I want 4 students, 4 times 3 times 2 times 1. So it's fundamental counting principle. I get 5 letters in the K, 5 times 4 times 3 times 2 times 1. So every time I try and arrange a different number of objects, right, because next up comes batting orders. Right? I want to arrange how many different batting orders. So for those not familiar with baseball, there are 9 players who bat. Okay, so at the top of the first inning, so baseball is divided into 9 innings, it's called the top and the bottom. At the top of the first inning, the visiting team comes to bat, right? So they're on offense. It's kind of a weird game that way. Usually on offense, the offensive team has the ball, like in football or soccer or handball or you name any other sport. But in baseball, it's the defensive team that has the ball. Anyway, so 9 players come up to bat in an order, and then the order repeats. So how many batting orders are there? Well, if we use the fundamental counting principle, and what the manager does is they submit 1, 2, 3, 4, 5, 6, 7, 8. They submit the lineup to the umpire and says, this is the order in which my players will be coming up to bat. And so for the first player to come up to bat, how many choices does the manager have? 9. And then, and what's another way to say that?
9.
In German, 9. 9. Okay, so this comes up a lot. What is there on our calculator that's going to do this? So calculator's out at the ready. So I'm not going to ask somebody to sit down like with 10 factorial and go 10 times 9 times 8 times 7, right? We're going to go 9. So you do a 9. Okay, you go to math. Hit the math menu. You go over to probability. So I can go to the right 3 times or to the left twice. If you have an older calculator, there is no frac menu. No fracking. Bad for the environment. Just go to the probability menu, and number 4 is the factorial. So there's 9 factorial. We hit that, we will get 9 times 8 times 7 times 6 times etc., which is 362,000. 362,880. All right, that's pretty close to 365,000, right? So you think about this. That's not far off 365,000. There's 365 days in a year. If that baseball team played baseball every day, and they could have a different order for just a little bit short of 1,000 years. Okay? So all we're doing is arranging those 9 players. And we say you could have, so if I divide by 365, we'll figure out how many years. If you played once a day, you could play for a little over 994 years before you had to repeat a batting order. That's kind of amazing, I think. Right? If it's 3 people, we know there's 6 ways. If it's 4 people, it's 24. If there's 5 people, it's 120. Right? You go 6, 7, 8, and when you get to 9, all of a sudden we're up to 362,880 different ways. Distinguishable arrangements, right? Ones that you can tell apart. Finish order of 6 students in a cross-country race. If Billy is the winner, and Billy's one of the students, how many ways can that be done? 5 factorial. So here's one way to think about it. So when I show you answers, I'm going to show you a fundamental counting principle way of doing it and a permutation way of doing it. Or when we learn the other thing, I'll show you that way of doing it. And the reason I just want you to see both ways, right? Because maybe for multiple choice, they list the answer using factorial notation. Maybe they list an answer showing the fundamental counting principle, right? So you need to just be familiar with, okay, let me be familiar with both ways. So if I said finishing order of 6 students, so the fundamental counting principle says put down 6 blanks. Then it says, put your first blank lower, it's too high. After that it says, are there any restrictions? Are there anything we need to know about? So what do we need to know? We need to know that Billy finishes in first. So this is going to be Billy. How many Billys are there? 1. So we have 1 choice for the first place student. Sorry, getting fingers out. Okay, so we have 6 students, right? Billy finishes in first. So how many students are left to go in second place? And then. Okay, so 1 times 5 times 4 times 3 times 2 times 1, which we could say is 1 times 5 factorial, which we could say is 120. Okay, so we set it up. So you don't really have to set it up as a fundamental counting principle. You can just say, all right, Billy, you're out of here. Okay. I have 5 other students to worry about, right? Sorry, 5 other finishers to worry about. How many orders can 5 students finish in? 5 factorial, 120. So that's another way to think about it, right? It's like, okay, there's 6 people there. One of them is Billy. You're gone, right? Move off. If it was like Scrabble tiles, just take that tile, put it aside. I've already dealt with you. What's left? Okay, so you can go 1 times 5 times 4 times 3 times 2 times 1. You can go 1 times 5 factorial. You can just think of it as, all right, I only have to arrange 5 others. It's just 5 factorial. All right, similarly, you got Henry, Henry, but the first letter is an H. How many ways? How many? So here's what I would do. How many ways can those be arranged? So 4 factorial or 24. So that's the way I handle stuff like that. So, all right, let's deal with the H is gone, right? I mean, really, legitimately, it is like Scrabble tiles. You've got Henry in front of you, and the H, that gets played, so now we're left with, okay. And another way to think about it, there are 5 letters. That one's an H. There is one H. Then there are 4, then 3, then 2, then 1, which is 1 times 4 factorial, which is 24. I was about to say, there's no wrong way to think. There are millions of wrong ways to think about this. But if you're just thinking about this correctly, then there isn't a wrong way by thinking, oh, it's going to be 1 times 4 factorial. Or it's going to be 1 times 4 times 3 times 2 times 1. Or it's just going to be 24. Now, the reason I go through all of these is I have no idea what they're going to say the answer as. So if that question is asked, the answers would be 24, correct answer, 120, let's just do the arrangements of 5 objects, right? Forget it, pretend they didn't know that, and pick 2 other numbers, right? With some reasoning behind them. Why would a student choose those numbers, right? Anytime we write a question, you have to justify an answer. Why would they pick this? Well, it's the correct one. It's the one we hope they pick. This would be if they forget that the H has to be first, so they think it's 5 factorial 120. I can't actually think of 2 more reasonable answers, so this would become a numeric response question and not a multiple choice question, right? So you need 3 reasonable distracted answers. So they could show the answer like this. They could just go 4 factorial. They could show it as 1 times 4 factorial. They could show it as 24. So you need to see all those ways so you can say, oh, they're showing it as number times number times number times number times number. That's using the fundamental counting principle. How do they do that? Oh, they're just showing it as a factorial. How do they do that? 7 friends sit in a row at a movie theater. How many ways? Which is? Don't do it this way. I'm working backwards. So you can put down 7 blanks. I have 7 friends. There's nothing special about them, right? As in, like in the next one, there is something special about them. We'll have to deal with that. We'll do that in a moment. 7 friends, they are distinguishable, right? So later on in this unit, what you have to ask yourself is, does the order matter? And if it does, it's a permutation. You're doing it this way. And if it doesn't, then there's another way you're doing it. So fundamental counting principle, 7 blanks. I got 7 choices, then 6, then 5, then 4, then 3, then 2, then 1. Or I'm arranging 7 objects. That could be done in 7 factorial ways. 50, 40. What if the arrangements of 7 friends that sit in a row at a movie theater, if Bobby sits in the aisle seat and Sally sits at the other end, and we're assuming Bobby and Sally are partners. How many ways? Just toss me a number. What's the number? 120. Everybody agree with 120? How do you get 120? 5 factorial. So you can just say, right? You can legit say 7 people. I've sat 2 of them down. I got 5 left to arrange. You can say, I have 7 objects to arrange. Bobby's got to be first. How many Bobbies are there? Likely 1. We're assuming nobody. How many Sallys are there? I have 7 objects to arrange. I've accounted for 2 of them. How many are left to go here? And then notice, and is associated with multiply. So you are always going to hear me when I'm doing a fundamental counting principle say this and this, except I don't say and, I say and then, because to me it sounds better. So I have 5 choices for the first, and then 4 choices for the next, and then 3 choices. And every time I say and then in my head, I put down a multiply. Every time in my head I say or, I put down a plus. So and is associated with multiplying, or is associated with plus. When you go to describe situations in this unit, you're going to have to use words like and. Even if you don't want to, you should use them, right? Because we would just say, you know, we get lazy with the language. We don't say there's 5 and then 4 and then 3. We say it's 5, 4, 3, 2, 1. Okay, what does that mean though? Do I add those? 5 plus 4 plus 3? Or is it 5 or 4 or 3? No, that doesn't make any sense, right? You can't have 5 or 4. You have 5 and then 4. Okay, which tells you, oh, I'm going to be multiplying them, right? I don't want to add these. When would I add them? Okay, we'll get some examples later on about when things become an or. When do I do an or? Okay. Let's flip this. And let's just say if Bobby and Sally sit on the ends. So extension problem, right? With more marks. How many ways did Bobby and Sally sit on the ends? Think about it and give me a number. So I'm only going to do this one way. I'm going to say I got 7 people. 1, 2, 3, 4, 5, 6. I got 7 blanks. I know that Bobby and Sally, unfortunate abbreviate. I know that Bobby and Sally are sitting on the end. Let's say this. Bobby or Sally. So if it's Bobby or Sally on this end, how many choices do I have for the first person? I have 2 choices. The other person. How many choices do I have for the other end? Just 1, right? Because it's Bobby or Sally. If Bobby's here, Sally's here. If Sally's here, right? This is Bobby or Sally. So if Bobby's here, then Sally's here. And if Sally's here, then Bobby's here. Okay, we've dealt with the restrictions, right? How many choices are there here? Well, we got 7 people in total, right? And we've accounted for 2 of Bobby's out. So what's the answer? So 2 times 5 factorial, or 240. So I would do this as a fundamental counting principle. Okay? There are my 7 blanks, right? Oh, one of these 2 people is on this end. That's 2 choices. Then the other one that goes here. After you put the person at the beginning, there's only 1 choice. The other person has to go on the other end. Okay, now let's go into the middle. What do we got left? Oh, 5 times 4 times 3 times 2 times 1. 10 different library books on a shelf. Can be done how many ways? What is it? 2, 6, 8.
Oh, yeah, no. 3, 6, 2, 8, 8.
3 what?
3, 6, 2.
I'll know this later. We do take the number of batting orders and stick a 0 on the end, right? Because we're just multiplying it by 10. So the 362,880 becomes 3,600,000. That's a lot, right? I mean, let's say you were arranging those books. And you could do an arrangement every second. How long would it take you to go through all the possible arrangements? All right, we can figure this out. Yeah. Okay, the obvious answer is a long time. So let's take 10, math, okay, over to probability, number 4. There's that. Okay, let's say how many days? So divide by 365. 9,941 days, or sorry, years. That's how many years? No, okay, wait a sec. Yeah, 300. No, that's how many days.
I thought you said seconds.
Yeah, well, we're getting there. We got to get there one step at a time. So now I've confused myself. So we have We have that many arrangements to make. If we divide by 365, that's how many days it would take, right?
No. That number divided by 60 would be the number of minutes. And then divided by 60 again would be
Number.
the number of hours. And then
Fine, one of us is on the ball.
then divided by 24 would be days. And then divided by 365 would be.
All right, let's start over. Take this number. Okay, so we're going to divide by 60.
That gives you minutes.
The minutes or hours?
Hours.
No, I thought you said that was seconds. 3,628.
No,
That's the number of arrangements. Okay, so let's say that is the number of seconds.
Well, you said
Okay, so divided by 60 is minutes, right?
Yeah.
Divided by 60 again is hours. Why am I doing this? I didn't have to do this. So that's how many hours. Divide by 24 will be days, right?
Yeah.
Okay. So we got days. So 42 days. So one arrangement. How long is a billion seconds? A lot. I have lived over a billion seconds. You guys are a little over halfway there. So a billion seconds is around. So if you want an idea of how big a billion is, it's 32 years in seconds. 1 billion seconds is 32 years. Okay, so what did we get down to there? It was 42 days to do all those arrangements? It's not bad. That's going 24/7, right? It's not bad. I could do that. Pay me enough. 32 days. We're done.